Impossible quantum teleportation achieved on normal internet cables. Northwestern University engineers made a remarkable advance in quantum computing and communication, demonstrating quantum teleportation over a standard fiber optic cable that already carries everyday internet traffic. This development shows that quantum communication might not require dedicated lines, which clears the path for easier and more widespread integration of quantum and classical data sharing. The news centers around the idea that quantum signals, information carried by delicate particles of light known as photons, can travel alongside everyday internet traffic without losing their integrity. This breakthrough demonstrates quantum teleportation, a process where the state of a particle, like a photon, is transferred to another distant particle without the initial particle moving physically. By using entangled photons, this method enables secure, near-instantaneous data sharing and paves the way for future quantum networks. The research team successfully tested a setup that allows quantum information to weave through the bustling flow of regular internet data without interference. This achievement overcomes one of the biggest hurdles in making quantum networks a practical reality. Prem Kumar, who oversaw the research, is a professor of electrical and computer engineering at Northwestern's McCormick School of Engineering. He is known for his contributions to quantum communication and serves as the director of the Center for Photonic Communication and Computing. In their recent work, Kumar and his collaborators introduce a new way of thinking about quantum signals alongside their classical counterparts. Quantum teleportation stands out because it uses entanglement as a way to exchange information without physically sending matter across a distance. The concept traces back to Einstein, Podolsky, and Rosen in 1935. Scientists have since tested quantum entanglement in labs, culminating in the formal proposal for quantum teleportation in 1993. One of the biggest appeals of quantum teleportation is that it can occur almost as fast as light travels. Photons can become entangled so that performing a measurement on one instantaneously affects its partner, no matter how far away it is. This is incredibly exciting because nobody thought it was possible. Our work shows a path towards next-generation quantum and classical networks sharing a unified fiber optic infrastructure. Basically, it opens the door to pushing quantum communications to the next level, enthused Kumar. Securing a clear route for single photons involves more than just adding them to an active cable. Ordinary internet traffic typically relies on millions of light particles, so a handful of quantum photons can easily get lost or overwhelmed. The Northwestern team performed detailed studies on how light scatters inside the cable to see if there was a specific wavelength that experiences less clutter. They pinpointed that sweet spot and added special filters to reduce the noise generated by normal data traffic. Quantum teleportation has the ability to provide quantum connectivity securely between geographically distant nodes, said Kumar. Past work suggested that large-scale quantum networks might need specialized systems. Now, his findings reveal that this might not be strictly necessary if signals are positioned in just the right place in the spectrum. Earlier demonstrations of quantum teleportation typically involved pristine settings, or dedicated fibers. Some researchers believed that real-world cables, teeming with signals, would smother the faint quantum light. That assumption has been proven wrong. In tests at Northwestern, the researchers ran quantum signals and classical communications over the same fiber optic cable without them colliding. They measured how well the quantum information arrived at its destination and confirmed that it was still correct at the other end. Our work shows a path towards next-generation quantum and classical networks, Kumar summarized. The immediate plan is to scale the system to longer runs and then transition to underground fiber connections. The group believes that an eventual shift to real-world cables could be next. Building on single-pair teleportation, they also want to experiment with multiple pairs of entangled photons to achieve another crucial step known as entanglement swapping. If that milestone is reached, quantum networks could begin to take shape across regions rather than only between 2 points. For critical operations in finance, defense, and data management, such networks could offer more secure connections thanks to the inherent secrecy of quantum methods, where any tampering is immediately noticeable. The capacity to support quantum connections without setting up special cables makes many new ideas more viable. Distributed quantum computing, which relies on linking multiple quantum computers in different locations, would be simpler to establish. Distance sensing tasks and advanced metrology could also benefit from more stable quantum links. Even beyond computing, quantum networks have the potential to spur new technologies in encryption, imaging, and fundamental physics experiments. Researchers have also discussed using quantum entanglement to synchronize distant clocks or to share random numbers for cryptography at unprecedented levels of security. Quantum teleportation has matured from a fascinating theory to a tool that is becoming more practical. While it is never straightforward to integrate delicate quantum signals, the Northwestern Group's accomplishment raises confidence that such integration is within reach. Many experts have believed that building specialized infrastructure was an unavoidable cost of quantum networking. According to Kumar's report, if wavelengths are picked carefully, classical signals and quantum information can coexist just fine. This line of thinking spares organizations from installing entire new grids of cables. In upcoming work, the researchers plan to expand the scope of their approach in longer segments to confirm that the method remains stable as cables stretch far past the lab. They will also design a multi-node demonstration to verify it can handle more than a single link. There is much excitement that existing communication channels, once tuned just right, could carry quantum data to distant points. With such possibilities on the horizon, quantum teleportation may shift from a theoretical concept to a tool that transforms communication. The future might see quantum and classical networks working side by side in ways that once sounded unlikely. The study is published in the journal Optica.